In February 2017, nearly 200,000 people were told to evacuate their homes in Northern California. The Oroville Dam, the tallest dam in the United States, had developed a growing hole in its spillway. For a brief moment, one of the country's largest pieces of infrastructure didn't look permanent anymore. The dam held, but the assumption that it always would cracked. This is worth knowing. When evacuation orders were issued in February 2017, the structure in question wasn't failing outright, but one of its components was. Oroville Dam, completed in 1968, is the tallest dam in the United States. It holds back Lake Oroville, a critical reservoir for water storage, flood control, and hydroelectric power. For decades, it operated without major incident. After heavy winter storms, large volumes of water were released down the main spillway. A section of concrete fractured, exposing underlying material. Flow was reduced for inspection. The erosion expanded. As reservoir levels rose, water approached the emergency spillway, a secondary overflow structure that had never been used. When water finally passed over it, erosion began almost immediately along the unarmored hillside below. That erosion, not structural collapse, triggered the evacuation of nearly 200,000 people downstream. The dam itself remained intact. The emergency spillway did not fail. Crews stabilized the structure before catastrophic breach occurred. Subsequent investigations found that concerns about spillway vulnerability had been raised years earlier. Questions about drainage capacity and reinforcement had been documented. Mitigation proposals had been evaluated and not implemented. None of these decisions appeared unreasonable in isolation. The structure had performed reliably for decades, but large infrastructure depends less on permanence than on maintenance, oversight, and updated risk assumptions. Oroville did not collapse. It revealed how stability can mask accumulated vulnerability. In June 2000, London opened the Millennium Bridge, a pedestrian suspension bridge spanning the River Thames. Within hours, it began to sway. The motion was lateral, a subtle side-to-side movement that grew more pronounced as more people crossed. The structure was not close to collapse. The materials were sound. The engineering calculations were correct within their assumptions. The issue was interaction. As pedestrians felt the slight movement, they adjusted their footing. Unintentionally, many synchronized their steps with the bridge's motion. That synchronization amplified the oscillation. The movement fed back into itself. Engineers had modeled wind load and structural stress. They had not fully accounted for synchronized human behavior at scale. The bridge was closed 2 days after opening. Over the next 2 years, it was retrofitted with dampers designed to absorb lateral vibration. It reopened in 2002 and has operated without similar incidents since. The Millennium Bridge did not fail structurally. It exposed a modeling gap. The difference between controlled calculations and real-world systems that include human behavior. Complex infrastructure is rarely static. It exists within networks of interaction. Even small, unanticipated feedback loops can produce visible stress. The bridge held. What changed was the understanding of how the system behaved under live conditions. Completed in 1936, Hoover Dam was built to control flooding, store water, and generate hydroelectric power along the Colorado River. Its design relied on river flow data from the early 20th century. Those projections shaped reservoir capacity, power generation estimates, and long-term water allocation agreements across the Southwest. For decades, the system operated within expected ranges. In the past 20 years, prolonged drought in the Colorado River basin has reduced inflows into Lake Mead. Reservoir levels have dropped to record lows. As water levels fall, hydroelectric generation capacity declines. Intake valves sit closer to minimum operating thresholds. Water delivery agreements between states are periodically renegotiated under shortage conditions. The structure itself remains stable. The pressure is not structural failure. It is sustained environmental change interacting with original design assumptions. Hoover Dam continues to function, but its performance now depends on updated allocation policies, conservation measures, and reduced expectations about river flow. Longevity does not eliminate constraints. It makes them visible. Completed in 2012, the Three Gorges Dam spans the Yangtze River in central China. At over 2 kilometers wide, it is the largest hydroelectric power station in the world by installed capacity. The dam was built for flood control, power generation, and improved navigation. It displaced more than 1 million residents during construction. Entire towns were relocated as the reservoir filled. Since completion, the structure has operated at scale, generating significant electricity and altering seasonal flood patterns downstream. But scale introduces secondary effects. Sediment that once flowed freely along the Yangtze now accumulates in the reservoir. Reduced downstream sediment transport affects riverbanks and delta regions. Reservoir weight has prompted studies on induced seismic activity in the surrounding area. Water level fluctuations affect slope stability along the reservoir's edges. None of these issues indicate imminent structural collapse. They reflect complexity. A system of this size alters the environment it is meant to manage. Flood control, power generation, sediment flow, ecosystem dynamics, and human settlement become interdependent variables. The Three Gorges Dam functions as designed. Its long-term stability depends on continuous monitoring, sediment management strategies, and adaptation to ecological feedback. The larger the system, the wider its sphere of consequence. On August 14, 2003, a high-voltage transmission line in northern Ohio sagged into overgrown trees and shut down. The event itself was not unusual. Lines trip offline regularly. Power is rerouted automatically. What made this different was coordination failure. A software alarm system at a regional control center failed to notify operators that multiple lines were going offline. As electricity rerouted, neighboring lines became overloaded. They tripped in sequence. Within minutes, the cascade spread across 8 U.S. states and parts of Ontario. Approximately 50 million people lost power. The physical infrastructure was not destroyed. Most transmission lines remained intact. The system shut itself down to prevent further damage. But the event exposed how tightly coupled the grid had become. Electricity must be balanced in real time, supply matching demand across thousands of miles of interconnected lines. Stability depends on constant monitoring, vegetation management, updated software, and coordination across jurisdictions. The grid works because it is continuously adjusted. In 2003, a single point of failure propagated through the network faster than operators could respond. Power was restored within days. The structure held. What shifted was the understanding of how interdependent the system had become. Infrastructure rarely fails without signals. More often, it operates quietly, under assumptions that must be revisited. Stability is not a permanent condition. It is maintained. If you're curious about how other systems operate under stress, there's more to explore here. This is worth knowing.